Have you ever wondered how a simple machine like a lever has impacted our lives? Curious enough? Then come with me. Come and learn more about the different types of levers and the science behind them. A lever is a simple machine. It can be as simple as a single unit like a spanner or a crowbar. It can also be a combination of moving and fixed components that transmit, change, or modify the direction or magnitude of a force by using leverage to multiply the force and do useful work. A lever is a device that consists of a rigid beam, bar, or rod pivoted at a fixed fulcrum or hinge. A fulcrum is a point at which a lever rotates. A hinge allows rotational movements between two connected parts. It allows two objects to pivot or rotate relative to each other around a fixed axis. The position of the fulcrum or hinge relative to the load and the applied force determines the mechanical advantage. A simple machine like a lever gives us leverage or mechanical advantage to lift or move heavy objects. Without it, some tasks are simply impossible. So, what then is mechanical advantage? Well, mechanical advantage simply multiplies the force to do useful work. The lever magnifies the force if the fulcrum is closer to the load than the effort. The multiplication or amplification of the force or effort defines the mechanical advantage of a machine. It's expressed as a ratio of the load to the effort. Therefore, mechanical advantage is equal to load over effort. Load can be expressed as L, effort as E. Now, let's do this. If a lever allows an effort of 200 newtons to lift a load of 400 newtons, then the mechanical advantage is 400 newtons divided by 200 newtons, which gives us 2. This is the actual mechanical advantage. It accounts for real-world inefficiencies like friction and heat losses. So, let the distance of the effort from the pivot be A, and the distance of the load from the pivot be B. Now, take note, a lever's mechanical advantage can also be determined by the ratio of A and B. To demonstrate this, let's use the principle of moments. A moment is a product of a force and the perpendicular distance the force is from the fulcrum. Therefore, a moment is equal to force multiplied by distance. Force is measured in newtons. It's an SI unit represented by the letter N. Now, if the lever is in equilibrium, then the moment on the effort side is equal in magnitude and opposite in direction to the moment on the load side. Like we said before, effort is represented by the letter E and load is represented by L. The moment on the effort side is E multiplied by A, which is EA. The moment on the load side is L multiplied by B, which is LB. In equilibrium, the moments are equal, therefore EA equals LB. If we cross multiply, then A over B equals L over E. But mechanical advantage is L over E, which we've just seen is also A over B. So, let's say the length of the effort arm is 6 meters and the load arm is 2 meters. We know that the mechanical advantage is A over B, which in this case is 6 meters over 2 meters. And it gives us 3. This is the ideal mechanical advantage, which is theoretical by the way, and is dependent on the lever's physical dimensions and assumes no losses such as friction or heat. So, if we have a load of 800 newtons and is 3 meters from the fulcrum, it gives us a moment on the load side which is 800 newtons multiplied by 3 meters, which gives us 2400 newton meter. Now, let's say the effort needed to move or balance this load is an unknown quantity E and it's 12 meters from the fulcrum. The moment on this effort side is E multiplied by 12 meters. This moment should be at least equal to the moment on the load side, which we know is 2,400 Newton meter. To simplify this equation or solve for E, we divide both sides by 12 meters. This cancels out, the two m's cancel each other, so E is now equal to 2,400 newtons divided by 12. This gives us 200 newtons. We bring back our lever. We can see that a minimum effort of 200 newtons, which is 12 meters from the fulcrum, is required to balance, move, or lift a load of 800 newtons, which is 3 meters from the fulcrum. Let's take note of the following. If the mechanical advantage is equal to 1, then the lever is in equilibrium. If the mechanical advantage is greater than 1, then the lever magnifies the force. If the mechanical advantage is less than 1, then the lever reduces the force. It should also be observed that whenever the mechanical advantage is greater than 1, then the effort travels a greater distance than the load. The comparison or ratio of these two distances is known as the velocity ratio. It's the distance moved by the effort over the distance moved by the load. Note that, as with mechanical advantage, a higher velocity ratio means the effort moves a greater distance than the load, but it also means less effort is used. Whenever a machine is put to work, it's essential to know how good or bad it performs. A measure of its efficiency is a good indicator. Here, it's clear to see that moving a rock using a crowbar is way much more difficult than using a wheelbarrow. In this particular case, a wheelbarrow is said to be more efficient than the crowbar. Efficiency is a measure or ratio of work output over work input. Work done is force multiplied by distance moved. Now, let's have a load of 200 newtons and say the distance moved is 2 meters. By the way, in a lever's case, bear in mind that the actual distance moved by the load is an arc length rather than a straight line. Anyway, let's proceed. Work output is 200 newtons multiplied by 2 meters, which gives us 400 Newton meter. The standard SI unit for work is the joule. It's equal to a Newton meter and is represented by the letter J. Now, back to our example. If we consider friction and other energy losses, we find ourselves applying and moving a force of 100 newtons over a distance of 5 meters. The work input in this case will be 100 newtons multiplied by 5 meters, which gives us 500 Newton meter, which is 500 joules. As stated before, efficiency is work output over work input. In our case, it's 400 joules over 500 joules, which is 0.8. But efficiency is always presented as a percentage, so efficiency is multiplied by 100%. Therefore, our efficiency is 0.8 multiplied by 100%, which gives us 80%. Efficiency can also be presented as actual mechanical advantage over ideal mechanical advantage. No machine has an efficiency of 100% or more because of energy absorbing factors such as friction, heat losses, sound losses, and even the weight of machine components. Moving on, it's important to note that there are 3 types of levers. They are categorized in classes according to how they operate and how they are configured. We have Class 1, Class 2, and Class 3. The position of the load, the effort, and the fulcrum determines the class. So, here we go. Class 1. The fulcrum is between the effort and the load. A good example is the pliers. Fulcrum in the middle of effort and load. A crowbar is another example. fulcrum in the middle of effort and load. Before we go to class 2, it's important to take a brief look at linked levers. Examples are pliers and scissors. Linked levers join two or more individual levers at pivot points to form a mechanism. We go on to class 2. The load is between the effort and the fulcrum. A good example is a wheelbarrow. The load is in the middle, the wheel axle is the fulcrum on one end, and on the other end, the effort is applied to the handles. A nutcracker comes to mind as well. The nut is the load in the middle, the hinge is on one end, and the effort is on the handles on the other end. We come to class 3. The effort is between the load and the fulcrum. An office stapler is a good example. The effort is in the middle, the load is on one end, and the hinge on the other end. A shovel or spade is another example. This hand applies the effort in the middle, the other hand represents the fulcrum or pivot on the other end. And obviously, the load is on this end. Let's go on and take a look at compound levers. A compound lever has two or more levers connected together to transmit or amplify a force. Unlike linked levers, the initial force applied on a compound lever is amplified due to the lever's mechanical advantage and then transmitted as an input force to the second lever. This accounts for huge force gains. To demonstrate this, let's say the mechanical advantage of lever 1 is 4. If we apply an effort of 60 newtons, then the output force is 60 newtons multiplied by 4, which is 240 newtons. This now becomes the input force to lever 2. Now, if lever 2 has a mechanical advantage of 3, then the output force is 240 newtons multiplied by 3, which is 720 newtons. The total mechanical advantage of the whole system is a multiplication of all mechanical advantages of individual levers. In our case, the total mechanical advantage is 4 multiplied by 3, which is 12. Note that 12 multiplied by the initial force of 60 newtons gives us 720 newtons. So, an initial force of 60 newtons ends up transmitting a relatively huge force of 720 newtons. This multiplication of mechanical advantages gives compound levers a big advantage. As simple as they may seem, levers have many uses. Some are lifting heavy objects, moving heavy objects, removing tight objects, and cutting. My name is Enoch Chambori. Hope you have enjoyed watching this video. Please like, comment, share, and subscribe. Thank you for watching Enoch Graphics.